Okay. Hi everyone, we're the microclimate team. Our team includes Yupeng, Zeyu, Sana-san, Zoro, Sean, and Vikram, and I'm Benjamin. So we're excited to share the progress we have made this semester. So our project is inspired by the NUS paper, Microclimate Spatial Temporal Prediction Using Deep Learning and Land Use Data. And in the work, the author introduced a geo-LSTM kriging framework that combines temporal sequence learning at weather stations with spatial downscaling on dense grid. And the approach uses a geo layer to adjust each station's temperature and humidity based on local land use characteristics, followed by an LSTM that predicts the next time step. A regression kriging step then interpolates these predictions onto a high-resolution grid to generate detailed microclimate maps. Overall, the study shows that this geo-LSTM kriging framework outperforms traditional interpolation methods and practical baselines, producing more accurate and spatially realistic microclimate predictions. But unlike the NUS paper, our approach doesn't construct surrogate history through spatial interpolation. Instead, we learn temporal dynamics directly from true station-level sequences using a multi-scale physics-aware model driven by solar geometry and diurnal features. Only after obtaining this physically consistent station forecast do we apply regression kriging to generate more than 100,000 point spatial field. The time-first base-second design avoids interpolation-generated pseudo-sequences and yields prediction that maintain real temporal causality while preserving high-resolution spatial structure. And this semester, our goal was to improve the model so it can generate higher resolution heat maps with many more grid points. As you can see on the image on the right-hand side, the image we produced last semester is only 1,000 grid points. And we also focus on refining our weather data preprocessing, because in our previous attempts, we discovered that a significant number of outliers in the training data. To achieve better model performance, it became clear that we have to ensure the weather data itself was cleaner and more reliable. In terms of data preprocessing, we made two major attempts this semester. Our first approach used weather data sourced from Weather Underground. The reason why we dumped the original data set is that the number of rows for each month was uneven. Our goal is to build a more uniform data set by supplementing it with data from nearby weather stations. To achieve this, we chose Weather Underground, which provides a more consistent and complete weather records that we can rely on. Here you can see the 3 weather stations located on the Georgia Tech campus. We use web scraping to collect their weather data. And this is a new data set we obtained through Weather Underground web scraping. It covers nearly 10 years of records and includes data from 3 weather stations on Georgia Tech campus. The dataset now contains variables such as relative humidity, temperature, and dew point. And on the spatial side, our grid system has also expanded. We now have over 100,000 grid points, compared to just over 1,000 in the previous version. And each grid point includes monthly shadow values. This gives us a far more detailed and comprehensive representation of the campus microclimate. And our first attempt at developing the machine learning model used Weather Underground dataset as an input for training. The dataset is split into training, validation, and test sets with an 8:1 ratio. The above figure shows the model temperature prediction performance on the test set. And overall, the model performs well. The root mean square error falls within an acceptable range. However, it is still higher than the training root mean square error, which was below 1. And the bottom figure shows the model's relative humidity prediction performance on the test set. Again, the overall performance looks good, but similar to temperature, the root mean square error is still higher. However, even though the data sets we obtain from Weather Underground are more consistent over time, they also come with a major disadvantage. The number of weather stations is still too small. We only have 3 stations now, compared to 16 in our previous setup. So this became a major issue for spatial interpolation. With only 3 stations, regression kriging frequently fails. So in practice, for an area the size of the Georgia Tech campus, kriging typically requires at least 9 well-distributed stations. And our configuration is right at the lower boundary, which is why the kriging solvers often collapse. So the status returned to our original data set, which includes more weather stations on campus. However, we still had to address the issues of uneven data distribution across different months. And Yupeng will take it from here.
Okay, so this leads us to return to our original dataset from Dr. Stone. However, we still had to address the issue of uneven data distribution across different months. So the questions became, how can we fix this imbalance while still keeping the benefits of original dataset? We came up with a solution. And here you can see the figures show month-by-month data coverage for each station across several years. The heat map reveals where readings are dense and where gaps occur, and the bar chart summarizes total monthly volume. And the main takeaway is that the warm season months consistently provide the strongest and most reliable coverage, while other months are sparse or incomplete. So this helps identify which periods are suitable for modeling. And here, we can look up the heat map where the groups the same data by calendar months. You can see it clearly shows the April through September form the most stable and well-covered block across stations. And the blue box highlights this warm season window. Based on this pattern, we plan to restrict our training and evaluation to those months where the observations are consistently dense and reliable. And here is my methodology. I trained on warm season data from 15 stations and reserved one completely unseen station for testing. And all data were reassembled to 10-minute intervals, cleaned for gaps, and converted into 24-hour input windows. Each training station was split chronologically into 90% for training and 10% for validation, and then merged into global sets. The model never saw a station ID, so it learned general warm season dynamics and had to transfer to a new site. And here I show our model development. For our training, we keep the core idea from TFT, which is temporal fusion transformer, but we adapted them for microclimate forecasting by using single-step prediction, adding parallel multi-scale LSTM branches, and relying only on physics-based features. This lets the model capture both fast changes and diurnal cycles while still generalizing to unseen locations. And here, as you can see, the loss curve drops quickly and then level off, with validation loss staying low and stable. The model shows no overfitting and early stopping selects the best points around epoch 23. The training is very smooth and converges cleanly. And you can see the temperature predictions closely follow the observations, capturing the full day-night cycle and matching peaks and troughs. And the humidity shows the same pattern with the predictions tightly aligned to the real values and no noticeable drift. And here you can see the training and the test RMSE are both low and nearly the same, showing strong generalizations. And for the residuals, you can see the residuals cluster tightly around 0, and predicted and actual values match closely, and correlations are almost 1. So the model is very stable, unbiased, and very accurate. So after training the model, we need to run the full inference plus regression kriging pipeline. So at each step, the fusion LSTM first predicts temperature and humidity at all 16 stations. And we then apply regression kriging to those station level predictions, expanding them to high resolution spatial field with no more than 100,000 grid points. And the temperature map on the left and the humidity map on the right show how sparse stations observations are transformed into smooth, physically consistent surfaces that align closely with the measured patterns. And here, the model handles the hottest, coldest, driest, and the most humid conditions in the dataset, and the spatial fields stay stable and realistic. This shows it performs well across the full range of weather extremes. And finally, we also analyze the importance of NAND use and NAND over features in the spatial regression. You can see the elevation explains much of the spatial variations in temperature, followed by the distance to parking areas and the distance to large buildings such as the library. And as for humidity, distance to parking, elevation, and distance to the library are the leading factors. So those results show the urban features has a clear and measurable influence on microclimate patterns.
Yeah, next I'll talk a bit about the API that we developed for Yupeng's model. So I worked on this part with Roshan and Vikram, and we also got a lot of help from Z, who actually helped us polish out the API from what we had and turned it into something that had visualizations. So here's where our progress is at right now. Um, I think the slide isn't updated, but basically we're using Fast API to house the model because the model itself is too heavy to run on Streamlit. And we needed to create a more efficient machine learning pipeline. And that's why we chose Fast API to provide sort of real-time access to the model's predictions and the maps. And the architecture is quite similar to Yupeng's model. I think we pretty much just implemented it and housed it inside like a server. And so we still use the Fusion LSTM model, the Kriging regression interpolation. And then from this, we can generate a visualization of the Georgia Tech campus map. And to operate the API, Rashan's going to show a little demo video, but basically to start the server, we just hit a command. And this is basically, oh, sorry, could you go back to the last slide?
Yeah, so the demo video is in the next slide, but essentially what happens is when you run the urecord command, you get the URL, the 127 URL, and once you go there, you're able to input the certain date and time you want the actual data and the prediction of the model to actually be generated for. And the original process was that it was sort of doing the actual and predicted temperature and relative humidity for like all of the data we had. And this essentially breaks it down to the actual day they wanted. And it helps reduce the runtime and generates the graphs to both the directory of the user and a downloadable JPG, and saving a lot of time for the user because that was the main point of us using the Fast API. I'm going to pass it on to Bikram now to talk about the next steps, but there's also like a implementation video in the next slide.
Yeah, so I guess we can play the video first.
Visualization all into a single backend right here. So what we're going to do first is we're going to start our server by pasting in the uvicorn command for Fast API service. It takes a few seconds. And as you can see, now that the model has been loaded and service has started, we can now go ahead and go to our localhost website within Chrome here. And you can see that this is the site for our model. And how we can test it out is by going to post section. And what we're going to do is we're going to input a JSON data of the time frame that we wanted to predict using the model. So here we have an example time frame of 2007, June 25th at 2 o'clock. So we're going to go ahead and paste it within this text box right here. Click on executes. It's going to start loading, and within a few seconds, you can see within our terminal that the model is currently being run. So pretty much for the backend, it runs the Fusion LSTM inference for the timestamp, and then afterwards it interpolates the results across the entire Georgia Tech campus grid. Then it generates the map of the temperature and humidity along with the comparison data. And then finally, it would be able to save the outputs and figures to a new folder and return the files as a JSON path. So Just give it a few seconds. And we will be able to see the results from over here, actually. And later on, it would actually give you an option to download these PNG files of the maps generated if you would like. But of course, the outputs themselves would also be saved within the directories or right here in the figures. So as you can see, the results are already out right here. Still taking a little bit longer to load on the site.
Okay, I think we can go to the next one. The one after.
We're at 17 minutes. If we could come to an end, otherwise.
Okay, yeah, so I guess I'll then quickly wrap it up. So the next steps essentially is how we can make it like production grade. We thought about 5 specific extensions. First one is security and authentication. We could write down the API. We can make it like more secure using like header-based authentication and stuff like that. And then you have containerization. Originally, we all had a lot of trouble running with different like Python dependencies and stuff before we got the unicorn command. So Dockerizing the application, this would help. And then cloud deployment. Another option of using Google Cloud Run or AWS Lambda or Azure. This way we can have it available 24/7 without needing to manage a physical server. And then real-time IoT integration. This is something we can look at for the front end. We can use like WebSockets to open a persistent connection to IoT weather sensors. And this way we can maybe make the data push faster in real time so that the updates can be refreshed faster. The last one is batch processing. So we could update the API so that it would accept greater batch requests, and so the program could run faster. These are the main 5 extensions, and I guess we could work on them like next semester.
Awesome. Are you guys done, or some more?
Yeah, I think that's all. I thought it was on the slides, but I guess it's not. That's all.
Okay. Thanks very much. Yeah, great updates, and thanks also for the updates on the API work. This is exciting.